Great. Well, hello, everyone. My name is Dija, and I'll be presenting about searching for dark matter decay to neutrinos with Gammaray and neutrino telescopes. So let's start at the beginning. As we all know, the standard model is great and all, but it doesn't account for all the physics phenomena that we see today. And for that reason, we need an extension to the standard model. So in particular, we're looking for a theory that can explain multiple phenomena at once. So that would be the observed neutrino masses and the nature of dark matter, or like we like to say, to kill two birds with one stone. So for that, WIMPs or weakly interactive massive particles are a simple solution to these problems. So we've already seen some astrophysical evidence, all hinting to gravitational effects about dark matter. So for example, galactic rotation curves, where we see a discrepancy on the rotational velocity of a galaxy, or also gravitational lensing, where we see distorted galaxies from an object of non-visible objects. So this just kind of motivates the hunt for the dark matter particle. We don't exactly know what type of mediator is in the middle, but exactly we're looking for dark matter and standard model connections. And we can look at that for different particular ways. So one way is direct detection or scattering, where we take a dark matter particle scattering with a standard model particle, and then we see the effect. We can also take collider production, like the LHC, where we take standard model particles with enough energy, we make them collide, and then we can produce dark matter particles. And the focus of this talk is indirect detection, which would be either annihilation or decay to standard model constituents. And like I said in the beginning, we're going to focus on neutrino final states. So that would be either dark matter decaying or annihilating to neutrinos only. So the good thing about indirect detection is that there's no need for a specialized detector. We can actually use gamma ray telescopes, neutrino experiments, or even cosmic ray experiments. And if we're searching for dark matter decay processes, it makes sense that we're looking into large reservoirs of dark matter. So this gives us two innuendos of what and where to look for dark matter. So on the what front, we have gamma rays, which we can see direct gamma rays either in space or as they arrive at Earth, we see how they interact with showers. One thing to note about gamma rays is that they get observed as they traverse the universe, so we need to account for that attenuation or absorption factor. We also have neutrinos, which are neutral and weakly interacting particles, so this is good, because as they traverse the universe, they don't lose, they provide great directionality of where they came from, and they can tell us a lot about the early universe as well. And then we have cosmic rays, which are a bit complicated because as they get close to Earth, they interact with the magnetic field. So it distorts those cosmic ray signals. So it's hard to pinpoint back its source. However, we can still use them. They're not completely bad. As we saw yesterday, there's a lot of extragalactic sources out there, like AGNs and other different galactic clusters. And we also have local sources like the Sun and the Earth in our galactic proximity. But however, I will focus specifically for dark matter coming from our galactic center or adjacent areas like the galactic halo. Now, we've already previously looked into dark matter annihilating to neutrinos. So this is the plot that we presented, setting the constraints for the average velocity average cross-section here. And some of the experiments will still be relevant for the purposes of this talk. So again, we focus now on dark matter decay to neutrinos. So just one simple particle decaying into neutrinos. So one thing I want to make clear early on is that we expect a correlated gamma ray signal due to electroweak corrections. So that means that we can take a look at two different type of signals. One is the prompt neutrino signal, which is simply, we just look for these two neutrinos coming from dark matter. Or we can also elevate this, or as I would like to say, complicate things with electroweak corrections, where we take this virtual process right here, and we get a gamma ray emission from here. I do want to specify that we still see the neutrinos, but now we have this additional gamma ray term. So how do we do this? So first we need to calculate this. So how we calculate it is with the flux from dark matter coming from our galactic center, and also flux from dark matter coming from our extragalactic sources. So for the galactic contribution, this is the flux equation. So let's break it down. First, we have the neutrino production spectrum. Usually we can treat this as a delta function. So simply we have the dark matter decaying into two neutrinos. But with electroweak corrections, it becomes more complicated. So here we have a plot of what that spectrum would look like for both cases. So on blue, we have the neutrino case, the neutrino signal, and in yellow for the gamma ray signal. Here I'm showing only the electron neutrino, but we do assume a 1-to-1 ratio of all flavors. We add all the fluxes together, and then we take an average of that flux to set our constraints. Now, this is the D factor. This is the astrophysical component of our flux. Everything else has been pertaining to particle physics. This is a 3D integral over the sky solid angle and line of sight. So this gives you a way of locating where your dark matter is coming from. And we use the NFW profile to define our dark matter galaxy density. So we use this to set some constraints then here on this parameter, which is the decay lifetime, the dark matter decay lifetime. Like I mentioned before, there's an extragalactic contribution that also plays an equal important role, but as we would expect, things again get more complicated, so I won't show it for the sake of time as well. But we expect an isotropic neutrino signal from all the other galaxies in the universe also that have dark matter decaying to neutrinos as well. So let's start with the neutrino signal. So in order to see this, we need to first detect neutrinos. So we've seen this plot before. It just shows you the measured and expected neutrino fluxes of extraterrestrial neutrinos. So for that, we need experiments. A very new that you haven't heard of experiments right here. IceCube is an ice Cherenkov detector. But the most important thing that I want to focus is that it has already measured a diffuse astrophysical neutrino flux in the TeV-PeV range. So I've made this kind of nice energy scale to kind of guide you along, because there's a lot of experiments, like as we saw on the flux plot, that can help us deal with this. So I'm going to mention a few, but a few is a few. So Borg-Xeno, starting from the low energy scale, we have Borg-Xeno and Camland, which are both liquid scintillators on the MeV scale. One looks for solar neutrino, and the other just more generically looks for extraterrestrial neutrino fluxes. Then we have Dune, which is a liquid argon TPC, looking for atmospheric neutrinos on the GeV scale. Down in the bottom here, we have Antares and Super Kamiokande, both water Cherenkovs, looking for atmospheric neutrinos on the GeV-TeV scale. Going up here, these are more perspective experiments. So we have P1 and Tambo, both water Cherenkovs, looking at the PeV scale. One looks for generic, again, extraterrestrial neutrino fluxes, whereas Tambo focuses on astrophysical tau neutrinos. And then at the ultra high energy scales, like EUV, we have Pierre Auger, which it was mentioned yesterday in Argentina, and also Brandt, which is, I believe, in China, just these big array setups that looks for tau neutrinos in this case, and then ultra high energy cosmic rays. So I just like showing those plots because it shows us not only the energy range and all the degree of colors here on the energy range, but also the different types of ways of searching for neutrinos. So, okay, it's a very busy plot, so let's kind of break it down. First, we have the solid lines, which are the current limits from current experiments. And then we have the dashed lines, which are sensitivities from these perspective experiments that are not yet established. So at the low energy scale, we have, for example, I mentioned Camland and Borg-Xeno. We just had to talk on Juno, so now you know where your experiments holds. We go up in energy in the mid-range. We have Dune, IceCube is Dipcore, Antares, and then going up in energy, now we have different sections like P1 Tambo, and then ending up in Brandt and Auger. And if you're an IceCube aficionado, then we also have the IceCube Gen 2. All right. So I mentioned that you could also see the gamma ray signal. So again, This means that due to electroweak corrections, which become relevant beyond the electroweak scale, we need a more complex calculation, which was done by Bauer, Rott, and Weber. It's a package called HDM spectra, if anybody needs it, that lets us compute the spectra of these neutrinos with the electroweak corrections. And for that, now we use gamma ray experiments. Again, they're all gamma ray experiments, so there's nothing fancy about them, other than their ability to probe different energies. So we have HAWK on the GeV-TeV scale. Then we have, which is a water Cherenkov. I guess that's one difference. And then we have LASSO, which is a hybrid air showers, has water tanks and also antennas on the GeV-PeV range. We have CTA on the TeV range, and then IceCube iSTOP. I know a lot of people mentioned the IceCube detector, but no one has mentioned iSTOP. So IceCube has some tanks and neon panels on top of some of the different positions that allows us to look for gamma rays and cosmic rays as well. And it's very important because it's also used as a veto for a lot of IceCube analyses. All right. So again, I didn't mention all of the experiments, but here are the results for the gamma ray experiments, where we have, again, solid lines for our current experiments and dash for the sensitivities on the gamma ray signal. And then bear with me, but we will put them all together. I didn't add all the experiments because it's a bit overwhelming, but these are the most comprehensive results that we have for dark matter decay into neutrinos. And I just want to mention that neutrinos are the least constrained channel of dark matter decay. So it's very nice to have these perspective limits for a wide range of experiments that we expect to see today. And yeah, that brings me to my summary. So sorry. So again, we have, I just presented the constraints over a wide mass range. So these will be published in an upcoming paper. So that's the very important thing that I wanted to say. So please stay tuned. And yes, now I'm done. Thank you.
Thank you, Dia.
Yep.
You didn't mention the Fermi satellite in your overview. Is this not
so Fermi
relevant?
is used here. It's used to set some constraints. I guess that's a question.
There's the green line. Okay.
So we don't use Fermi telescope to set some constraints, but it is used to set some extension for the extragalactic contributions from the gamma ray experiments. So essentially anything beyond the Fermi extension, it's not relevant for the extragalactic contributions for the gamma ray experiments. However, we do have a more complicated calculations for the neutrino, extragalactic neutrino signals. But yeah, okay. It's just simply used for that.
Thanks. Any further questions? Okay.
I didn't really get, sorry. What are you assuming? You assume that the branching ratio is the same for new E's, new mu's, and new tau's, and then you are averaging over. So what's the, I mean, in the case of the decays, the case equally to new E, new bar, new mu, new bar.
So we do take, so we don't make any assumptions about any branching ratio between the neutrino flavors. What we do is take a complete flux. So it would be like the sum contributions of each of the neutrinos. What it is different is that each individual flux will be different because for each particular flavor, with electroweak corrections, this neutrino spectra is very different. For example, for tau neutrinos, it's incredibly different.
And did you account for that? Yes.
Yes. So we compute the fluxes individually and then sum them up to set the tau decay lifetime as the most constraining number. We could do it per flavor, but we decided to do it more generally for all flavors, which means summing over the fluxes.
Okay.
Okay, yeah, one last question.
Sorry, this might be a very naive question. So you talked about the gamma ray signal, and is there a significant background from the neutral pion decays in the atmosphere?
From nuclear?
Neutral pion decays.
So it's essentially one of those that we expect to see. So this is all happening not inside the detector volume. So these gamma rays come from these nuclear pion decays from the proton pion decays on the outside. So we use them to locate our neutrinos. So if you see the gamma ray, but you don't see any neutrinos. There's a percentage or like probability that it's correlated to this interaction.
All right.
So, so these gamma ray experiments are completely unaware of the neutrinos. However, we can say, or we can expect them to be from them. So yes, this is all happening in our galaxy, but not inside our detectors. So.
Okay,
yeah.
thanks.
Okay, let's thank Dia again.
Yeah.
And